Welcome everyone to this introduction about one of our newest developments, the wound healing application. Personally, I am very excited about this fascinating new tool because it is fast, robust, and really easy to perform. Wound healing assays are mainly used to analyze the migration of cells, a process that is involved in a lot of physiological conditions like wound repair, immune response, or tissue remodeling. But migration is also relevant in pathological processes like cancer, invasion, and metastasis, and therefore assays analyzing migration could be an interesting readout in the screening of drug candidates. Among these assays are wound healing assays, in which an artificial wound is generated in a confluent monolayer of cells by creating a cell-free gap. The surrounding cells now start to migrate into this gap and eventually close it. This wound closure is monitored over time using either live cell imaging or by finding the exact same wound area at different time points using conventional microscopes. However, most of these assays are either time-consuming or only a few samples can be measured over time. Therefore, our aim was to develop an application suitable for automation and high-throughput screening using our images and YT software. To do so, we developed two-phase measurement design. In the first phase, an overview of the wound is imaged using a low magnification, usually the 4x objective. This keeps the measurement time and amount of data low. Already during measurement, an image analysis algorithm called Wound Healing ROI Finder detects the cell-free area and creates a region of interest in it. Only this ROI is then used in the second phase, where we usually use a 10x objective. Merely the second phase is needed for all subsequent time points, making the imaging very fast. Usually, we need less than a minute for a 96 well plate. The images of the second phase are automatically analyzed by YT software and result in different parameters. Here we see a summary of our experimental protocol. At first, we seeded cells in microplates. Then we created wounds using different techniques. One was a so-called scratch assay, where a scratch is created in the monolayer of cells using a sterile pipette tip. But we also used commercially available silicone inserts, which need to be removed to create the cell-free gap. Examples are the RS migration assay, which uses circular inserts, and another one are culture inserts 2-well and 4-well from EBD, which employ inserts with microcavities divided by small rectangular silicone walls. After wound creation, we immediately imaged the plates using both phases of the application. Then we treated the cells with cytochalasin D, which inhibits cell migration, and monitored the wound closure at regular time points, now only using the second phase of the application. In this slide, we see an overview of the assay results and example pictures of the two phases. In phase 1, the application robustly detected all kinds of wounds. It was even possible to detect more than one wound per well, as it is necessary for the culture insert 4-well from EBD, which has 4 little microvels. Even if these inserts were rotated, the software robustly detected the wounds. The ROIs, which are these little boxes, are then imaged in phase 2. Here in the well overview, we can see how much smaller this part is. It's especially obvious for the EBD inserts, which were measured in 24 or 12-well plates. Now I want to show you an overview of a scratch assay plate directly in the software. If I zoom into a well, we can see the cell-free area, which is now marked with a yellow line. This green box is the wound healing ROI that the software automatically places inside the wound. The white box is the cell periphery, which you can later use to calculate the relative wound density. Now, if we look at different wells, we see how robustly the application detects the cell-free area, even if the scratches are rotated, crooked, or of uneven width. In the second phase, the software automatically only scans the areas of the well in which the ROI was detected. It images it using as little sub-images as possible. Here you see that we have more than one measurement in this phase. If we go back to the first measurement, we see the original scratch, and then we can observe how the wound closes over time. The software automatically determines the confluence of the cells in the green box, which was the original gap, as well as on the periphery. Moreover, it detects the cell fronts, and from that it determines the average gap width, which is shown as a red box. We can observe the wound closure over time at one glance using the time charts of the Analyst tab. In column 2, we have the untreated cells, while in 3 we have the highest concentration of the inhibitor. As an example, we see the confluence on the gap. For the control-treated cells, the confluence increases over time because cells migrate into the stretch, while in the wells where cells were treated with cytokalism D, not much happens. The data can then be exported and further quantified using statistical software. For example, to calculate dose response curves, as you can see here. As I mentioned before, the EBD inserts have different microvels and are therefore also suitable for co-culture experiments with more than one cell line. Here we stained 2 different cell lines with cell tracker red and green and co-cultured them. The software can automatically create these galleries. We saw that in monoculture only the red cells migrated into the gap, while the green ones did not really move. However, in co-culture, more green cells started to move into the gap, which was an unexpected finding and will now be further analyzed. Let me sum up by highlighting the benefits of our wound healing application. The 2-phase measurement design and a robust laser-based autofocus enables very fast imaging and analysis suitable for automation and high-throughput screening. Precise image processing detects wounds of different number, size, width, shape, and orientation. And finally, the analysis is label-free and therefore non-invasive. As I said before, I'm personally very fascinated, and I think it's a very cool and helpful application. So I hope that maybe some of you get interested. Thank you very much for your time, and let us know if you have any questions, ideas, or remarks, or if you are interested in a demo.